Good morning to everyone. And so please take a seat that we will start in a few minutes. And I know that it's difficult with this nice weather today, and mainly for people coming from north of Europe. So, but if we do well, we will have time also to enjoy the coffee break outside and to take some air and sun. So, just some minutes more. Okay. Okay. In this second day of the meeting of this workshop, we dedicate time to make new synergy for networking and also to have new insights from other projects working in some topics that are related to the topics that we treated in an SDGs-EYES project. And we decide to invite people working on two main topics. The first one is on cities, urban environment. The second one is ecology and fires. And here with us there is Rodolfo Sardone. Rodolfo is the first speaker of today, and he came from Taranto. Taranto is a city in Puglia, very close by, and he's the director of a group of research in the ASL, that is Azienda Sanitaria Locale of Taranto City. And he will present the activity that they are leading on the integration of urban of data on urban environment, pollution, and also population health. So the floor is yours, Rodolfo. And
okay, I don't know if I have to talk here or
you can come here and so.
Okay, just to use the slide control.
We don't have any pointer.
No, so I think it has to be like this.
Start.
Okay. So thank you for the invitation to this magnificent meeting that basically is something that also is required by the policy of Horizon EU funding, because I'm from the local health authority of Taranto, that is the, let's say, public health authority in the province of Taranto, that means a coverage of more than almost 1 million of inhabitants. But I'm also the director, the scientific director of a project that was funded by Horizon EU in 2022 on the cluster environment and health, that is the Mistral project, and also the Calliope project that is funded by the Ministry of Enterprises of Italian government. Basically, we did a sort of platform, research platform, that has several projects that are conducted in the city, in the area of Taranto, but they also involve other partners all around Europe and world also, because we are also including Canadian partners, friends, particularly with the University of Krakow for the city of Rybnik, that is a city similar in terms of, let's say, doom of environmental exposure, particularly air pollution exposure, and the city of Hasselt-Genk, where there is the University of Hasselt and TU Narok that is working with us in the detection of new biomarkers for air pollution and more generally, more broadly, the entire system of different matrices of pollution and the effect on population health. Basically, Taranto is located in the very south of the Apulia region. It's quite near to Lecce, more or less 1 hour driving by car. It's very long heritage in terms of Greek heritage and architectural monuments and other things from the Spartans colony of Taras, that was the origin of the city. Is completely surrounded by the sea, but we had in 1961 the biggest steel plant of the entire Europe. Is now the production of steel is now stopped because of several issues specifically due to the let's say health impact on the population. Basically, in 2012, the prosecutors and police stopped everything because of very let's say very slightly effects on population health, particularly mesothelioma and other type of cancers related to air pollution. This means that we have a sort of interrupted real-time or real-world interrupted series analysis, because we have the retrospective data from the 2010, more or less, and the prospective data until now. What we build is a sort of consortium, a sort of public-private partnership that include not only research institute and local health and other type of authority like ARPA Puglia, that is the Environmental Protection Agency, but we also involve several companies, particularly startups, because the final ideas of the Calliope project, that is the project funded by the ministry, was to build up a sort of network of sensors, innovative sensor that could measure outdoor and indoor air pollution and could relate this type of data with the health of population. But we are also integrating several data from the satellite and other type of remote sensing devices. The idea is to build up this platform that aim to the protection of the One Health. I'm pretty sure that is not needed to explain you what is One Health, but the final scope of this project is to build up a sort of urban exposome of the city of Taranto. That means that we are collecting different type of human tissues, but also some samples from the matrices of the soil and the water, and also the quality of air of the area in which those people are living. Basically, the urban health is a new concept, but is basically something that is related also to health equity, because sometimes the people that are most exposed in the urban area are people that have the biggest health inequalities. Therefore, we are aiming also to the social status and the social background and economic background of our city, just to have a clear idea not only of the impact of population health, but also the economic and microeconomic impacts of air pollution and other type of pollution that we are analyzing, we are investigating. Everything started from the MR project, that is the project that I mentioned before. It's been funded for 5 million, more or less, and includes all those countries in Europe. The idea of a MR project was to build up a sort of digital twin of the 3 cities involved into this project, building a sort of simulative scenario in which we can simulate policies, interventions, and calculate with a quite, let's say, long-range forecasting the effects in terms of health and also health economics specifically. We also built with the Calliope project the entire infrastructure, that is the Urban Health Center that is located in Taranto, and where we work together for the collection of new samples of the people. It's a sort of perennial biomonitoring of the population of Taranto, and we do everything in the same place. So we have several devices, also a biorepository in which we store all the matrices, not only human tissues, but also environmental matrices. And we are also now implementing new devices also to make directly the analysis into this facility. Particularly, we are now conducting a new study, a sort of branch of the MR project that is more related to the neurodevelopmental disorders of the children, specifically collecting not only urine and blood, but also stools to have a clear idea of the, let's say, the microbiome of these individuals. This is a prospective study that is just started, and we are also using several innovative devices with the possibility to collect, for example, blood samples, not using the vein puncture for children, but just the finger punch that is quite simpler for, let's say, to involve children, particularly healthy children, to have a good control for the children that has some disorders, neurodevelopmental disorders. We also do all the analysis in a local high-performing computer. We have several workstations and HPC with which we are also modeling not only the, let's say, the association between pollution and health, but we are also modeling the entire air pollution or let's say air dispersion model. We did it with several companies, including Arianet, that is one of the biggest company in Italy that are able to do very complex air pollution monitoring, and we did a sort of very long-range air pollution exposure model that integrate different type of data, including satellite data, but at the end of the line, we have a sort of personal exposure of each resident of Taranto for 10 years. We also made some, let's say, biological analysis specifically on black carbon. With the Hasselt University, we developed a sort of technique with the confocal microscope to detect directly in the tissue the black carbon. We are doing it in the entire population, 2 neighbors of Taranto that are more, let's say, exposed to the steel plant. We are now doing it on the urine sample of the entire group of people, particularly families. We did the same into a brain biobank of Antwerp. We make this paper recently, and we demonstrate that black carbon in exposed people could be found also in the brain tissue directly. We also did several publications that involve also different type of urban pressure, urban stressor, including the greening, using different type of satellite analysis, but basically we are using the famous NDVI to investigate the association with mortality generally, but we are also doing some specific analysis on the type of diseases that could be related to the green, not at national level, but we are doing it at urban level, so at city level, let's say in this way. We did this type of citizen science platform that is Urbania, with which each citizen of Taranto could have the access and monitoring the personal risk to air pollution exposure, and also for technical operator, everyone could use the data that we are generating with the 45 sensors disseminated in the area of Taranto that are measuring continuously PM2.5, PM10, NO2, SO3. And also we developed this specifically designed sensors that are, let's say, disseminated in the area of Taranto. We are not just concentrating on outdoor pollution, but we are trying also to develop a model that includes also the indoor pollution. At the moment, we have 20 indoor sensors in the families that we are biomonitoring in the neighborhood of Taranto. We also created this public laboratory to qualify the sensors, the new sensors. This is very important because we have several startups in Taranto that are developing different type of sensor. For example, we developed a sensor that could continuously measure the radon gas. It's very important because you know that radon gas is a sort of new emerging, let's say, pollutant and is related to several diseases and is considered in the recent literature like the new asbestos. We did this lab for qualify the sensor that are developed locally. It is very important because it also qualified the quality of the data that are generated by those sensors. It's completely public. So the people that are approaching to this new lab are not paying for anything. It is very important because it's also assure the quality of the data that, let's say, citizen-oriented sensor could be could create. We also have a drone that is used not for air pollution directly, but it used for the light pollution monitoring. We are also concentrating on artificial light at night. We are making a sort of night map of Taranto to develop a model that could be used in the, let's say, investigation of the effects of artificial light at night with the human health, particularly with the sleep disorders and some type of mental issues, mental health issues. We also made a noise pollution map. It's quite, let's say, primitive at this moment, but we are now developing with some Canadian partners from the Sherbrooke University a model that could be related to the personal exposure of indoor and outdoor noise pollution using specific MEMS qualified sensors. You know that air pollution is one of the biggest topics in the last 20 years, but noise pollution is now emerging, particularly in the combination with the air pollution for, let's say, pollution derived from urban traffic. And you know that also probably it's one of the most important risk factors for hearing loss. And hearing loss is the most important risk factor for dementia, modifiable risk factor for dementia, as you can see in this slide that is from Livingstone, from the Lancet Commission on Dementia. We are also doing something on the sea. It's not, let's say, right place to talk about this, but it's very important because we are also monitoring the quality of the marine environment, specifically on the let's say, different contaminants, including PCB and PFAS. All those data are gathered into, let's say, a local server, local HPC, and we are modeling it with AriaNet, one of the partner of the Calliope project, in a data fusion model that could be, let's say, related to each inhabitant of Taranto. We also did several citizen science initiatives in Taranto, but also in Poland that involve directly population in collecting samples. You can see here some children that are working with the National Research Council researcher in collection of samples in the marine area of near to the let's say urban agglomerate of Taranto. And we created this huge data sets that include also some climate feature, particularly the land surface temperature that is measured using a sort of mixed model that includes satellite images but also ground-based sensor. We did this model that could be related to the personal exposure. This is very important because it's the first attempt to develop a model with a scale resolution of 5 meters. Is useful not only for epidemiological reason, but you can see that it could be used also to simulate policies, particular policies related to the greening of the city and urban green. We build the final output of the MR project, that is this digital twin. Now we are concentrating on creating greening policies and assessing the health impact on we're forecasting for 3 years, so we can just plant or simulate the plant of different type of trees, different type of plants and other green things, let's say this way, and we also can calculate the difference in deposition of PM2.5, PM10, NO2, and all the pollutants that are, let's say, related to the human health. We also did a very interesting study on a heat island in Taranto using this type of data fusion model. We had in July 2020 73 to 131 deaths in 3 days. We had a very high temperature, particularly during July. We can reach also 48 degrees Celsius at land surface temperature. And we did several initiatives as a public health authority using a sort of proximity approach in which we involved GPs, general practitioners, to protect directly people that could be exposed to heat island, particularly children and elderly. And we had a very important reduction in the July 2025, considering the same temperature. So it was a sort of very practical, pragmatical approach that saved several lives during the 3 years of observation. We also won this very fancy, let's say, award in China in the first international conference on climate leadership that was organized by the Harbin Institute of Technology, but also UCL. And we presented in that conference, but I can also present you a bunch of data about the biomonitoring of the city of Taranto. You can see here 2 different neighbors. The neighbors you can see on the north is very near to the steel plants, is the Tamburi neighbor. It's pretty famous because it's usually covered by dust, iron dust, so red dust. And the people that are living there are more exposed than the people that are in the area that you can see in south, that is 10 kilometers far from the steel plants. So we are creating this, let's say in this way, case control approach, biomonitoring, which we have the same population with the same social background, considering that the neighbor of Tamburi and also the neighbor of Tramontone has very low education level and very low social economical status, and we are collecting directly the families. So we are involving families in this biomonitoring, starting from the children, and then collecting data about their parents and grandparents. So a sort of family approach, biomonitoring that is very useful to detect also some, social patterns that could be related to human health, that could interact also with the air pollution. We had several output in this slide, but the most important one is that the mean education and the median education of the population is quite low. Because more than 50% of the population didn't reach the middle school education. So it's quite low for Italian city, and it means that there is a very important, let's say, issue about the inequalities in terms of geographical inequalities, but also health inequality. We also create different type of models and add different type of approach to detect the health effect. This is one approach that considers the statistic unit, not just the people, but the polygon of the map. It could be used to detect also not only the effect on human health, but also the economic effect of the environmental pressure, let's say in this way. Those are the preliminary results of the association between air pollution and other type of covariates, including, for example, the gender and the mean age, with the different type of health outcomes. You can see here one of the most interesting is that the NO2 has a very important positive association, so it's associated to the risk to have a dementia in 10 years. It's quite, let's say, widely known in the recent literature, but one of the most important discoveries that we also have hearing loss associated with NO2. This means that we are now to develop a model that consider not just the air pollution, because you know that hearing loss could be also related to the noise pollution. Therefore, we are now modeling also the urban noise to have a multi-pollutant model that could be used also in practical policy intervention. This is very interesting results about the microeconomic impacts. We are not just monitoring the health, but we are also monitoring the economic impact, because you know that steel plants in Taranto, there is a wide discussion about the trade-off between health and also the work, let's say, of the population that is working in the steel plant. So we also developed this microeconomic impacts model that somehow relate the increase of PM 2.5 and NO2 with the decrease of the new companies in 10 years, but also decrease the mean annual income per citizen living in the area that we are analyzing. We also did some analysis considering different types of urban pressure feature, including the NDMI, that you probably know it's more related to the, let's say, moisture than the greenness, considering that Taranto has very low NDVI, mean NDVI, because the green in the city is quite, let's say, rare, uncommon. We also have some association between the combination between NDVI, NDMI, and also PM 2.5 and LST. So we built this very huge model that could be has been approached with a statistical learning modeling, but was not so useful because the interaction between the covariates, between the feature, it's quite, let's say, unpredictable. Therefore, we use also a machine learning approach, a random forest, random survival forest. And surprisingly, the most important predictor is not the NO2 or the air pollution, but is the land surface temperature. You can see the land surface temperature on the fourth quartile, that means to have been exposed for 3 summers to a temperature that is above the 48 degrees. That is one of the most important predictors in mortality overall. So that's it. Thank you for this opportunity, and I'm open for questions.
Thank you very much, Rodolfo, for this impressive presentation about many aspects that touch urban health, population health. And when we touch population health, we all are very sensible and sensitive. And yeah, that's very good. Maybe I leave the floor first to people for questions, comment.
Thank you very much for the presentation. How do you communicate the results to the population, and how is it perceived? I mean, what do you do with the results in relation to the people living in Taranto?
Yeah, thank you. Is one of the probably the most, you touched one of the most important point, because you know that risk perception of air pollution sometimes is misperceived, particularly in people that are, let's say, a very long narrative of air pollution exposure. So it was quite complicated. We tried firstly to involve all the policymakers to understand which is the best way to communicate the risk, but also in parallel we also did several citizen science, let's say, engagement directly in the neighborhood that we studied. The final communication will be not at this level, at this technical level, but we develop specifically a platform for the citizen in which they can have the direct access and see the, let's say, the air quality index, for example, or other type of aggregate indicators for the air quality. I can say that when we started the project, we were quite worried about the impacts on the perception of the risk of population, but the population of Taranto was quite, let's say, habituated to this type of studies, and now we are completely involved. And sometimes we have several direct interaction with association of citizens. For example, we use the churches. So we started, for example, in this type of social aggregation entities, and we are communicating with them directly. On the other hand, they feel protected by our study because it's a continuous biomonitoring. So they feel protected because we are doing several clinical examinations that are directed to those neighbors. So we are trying also to, let's say, communicate a sort of general aim of the study to decrease the health inequities, because all those people are living there not just for chance, but in those neighbors, particularly in Tamburi neighbor, where, let's say, designed by the past urban designer as a sort of working class service area for the steel plants. So they are there not just for chance, they are there for a reason, and therefore we are concentrating on that population, also increasing the type of health services that we can, let's say, deploy with the local institution.
Fabio?
Thank you so much for this impressive presentation. Lots of data, lots of work. I just have a curiosity about the way in which you are treat the time. So, because basically, if I could understand correctly, the estimation of Poisson was based on a cross-section, or with the time. This is the first question. The second one is, when you try to assess on the effects of some policies, such as more green, or you in a way you are comparing, as you said, a previous situation with a further situation. But did you make some econometric exercise, such as diff and diff or something like that, to make to assess on the property of these differences? Thank you so much.
Thank you. Good points. The first one, yeah, we are considering the time because is for the retrospect we have two branches. The first one is a cross-sectional analysis in which we have just, let's say, collected two different data sets, one from the neighbor nearest to the steel plant, and one that is more or less similar in terms of socioeconomic status, but quite far, in 10 kilometers far from the steel plants. This is still ongoing, so it's cross-sectional. We plan follow-ups every 1 year, and we are doing it. We are in the first year of follow-up. We have no data, longitudinal data in 1 year, but basically we have no particularly change it during time. But we also have the entire population in 10 years of observation and air exposure, air pollution exposure. So we are considering time like a variable related to the single individual. So the quasi-Poisson regression was a longitudinal, let's say, approach in which we also considering time. We use quasi-Poisson, probably you know, because we are using as outcome the counting of death or events, but we are also doing Cox regression, for example, using person time variables, but we are also using machine learning like random survival forest that considering also the time as a covariate in the entire model. So time is quite important. It's complex to model when you have time, because you know that sometimes particularly for the climate exposure, sometimes could not vary so much. And in that case, we are just using the seasonal average exposure, for example. So we basically skip the winter in Puglia because we have no winter in Puglia, basically, anymore.
If you want, you can test in other city your model. We have winter in Turin,
yeah,
so
indeed,
no worries.
compare with the North European partners, we have the opposite effects, but we are considering time for the economics or health economics impact. In this project, we are using very simple microeconomic output or outcome like new enterprises, so personal wealth and, for example, waste taxes or that type of data that we could detect, let's say, retrospectively. But we are also collecting cross-sectional part, several data about their perceived, let's say, wealth or quality of life, and we are building a sort of model that could be used also for the retrospective database, deriving the quality of life to integrate into daily, for example, as a microeconometrics or health economics measures. But we are not concentrating in other type of econometric measure, but we are open to discuss, because this data set is now open to other type of collaboration. So if you have some ideas that we could implement in the model, we can do it easily. Thank you.
Yeah, I think it's maybe Teresa wants to comment, or my colleagues of CMCC, because in this SDGs project we have a pilot that now it's a service on urban health, stress and population. And Teresa Spadea from ASL Torino, she helped and she worked on risk analysis, and colleague from CMCC on the division on regional forecast. They work on climate part. So, Teresa?
Yeah. Hi. Yeah. Thank you for your presentation. As the others said, it was very impressive, and I think you have done everything you could do. So maybe what we have done was Manuela was mentioning is a risk assessment tool based in Turin at the micro area level, which is census tract, as you know, and the CMCC colleagues developed either new climate indicators. So maybe the only thing that we can offer and make a joint venture working on these new climate indicators specifically for the heat-related risks on the population. And we work at the aggregated level, not at the individual level, as you said. Also because we think that with this tool, we aim to identify areas most at risk, and the risk takes into account vulnerability in the sense of social indicators of socioeconomic position, and also urban characteristics of the area. So, I mean, maybe there is space for collaboration. In fact,
absolutely yes, and I could also take the, let's say, the ball for this opportunity, because in the next Horizon EU work program in the 2027, if I remember well, there is a specific call on climate and health or population health. So we are totally open to collaborate. We are starting to let's say involve other partners to create a consortium, and so I think that could be very useful for
very happy.
Reciprocally to have this type of collaboration. So thank you. Absolutely yes. We are it's open, totally open to collaboration.
Thanks.
And of course the great part of the project, we have different services. One is more on population health risk, but we have also other service on based on Earth observation, like forest classification, land degradation, fires. And I talk a bit with Feliciana in Barcelona, and I think we are there is room for next and further collaboration, and also for replicate things, because what we need also is replicate and compare our methods. Thank you very much, and Rodolfo will stay with us also for the panel later on, but you can take a seat here now, because so it's easier to follow the next presentation. And now we have Jessica Ruijsch. She will talk about biophysical climate effects of land restoration in Africa. Jessica, she just finished the PhD at the University of Wageningen, and now she starts working at the University of Ghent in Belgium, and she did a PhD on land degradation and restoration in Africa. Thank you. Jessica, the floor is yours.
Yes, thank you very much for the invitation. And indeed, my name is Jessica Ruijsch. I think you already said I currently work as a postdoctoral researcher at Ghent University in Belgium. But here I will mainly present my research from Wageningen University that I also did with the collaborators you see at the bottom. So in Africa, land degradation and climate change are already impacting the population in Africa. So, for example, it has a negative impact on food production, on biodiversity, but also on health and the general livelihood of the population. And many organizations, they recognize these threats and they propose a solution of land restoration. And this can be many different things, but it mainly consists of combating land degradation, and this usually comes with an increase in vegetation cover. So this can be things like tree planting or natural regeneration, area protection, these kind of things. And quite often these projects are implemented to combat land degradation, for example, but also, for example, to increase biodiversity. And very often it's also included in this kind of carbon credit system, so you can compensate your flight by planting trees somewhere. And because of the increase in vegetation, this can store carbon emissions, and therefore land restoration can have an effect on the global climate. But what's often not considered is that due to the increase in vegetation cover, land restoration can have a very direct impact on the local climate through so-called biophysical effects. And what do I mean with this is that usually the incoming solar radiation is either reflected or absorbed by the Earth's surface, and the net available solar radiation is brought back to the atmosphere in the form of evaporation, so the latent heat flux, this is called. And this is because the evaporation of water due to the vegetation, it needs energy, right? And the remaining part is brought back to the atmosphere in the form of the sensible heat flux, which is basically the transport of heat. And if you increase the amount of vegetation, this works in a similar way, but there are some major differences. And that's that with a high vegetation cover, the surface is usually a bit darker, which means there's more energy absorbed by the Earth's surface. And therefore, both these energy for evaporation and heat increases. And as a result, the temperature can increase. And this is referred to as albedo warming, because albedo is the amount of reflected solar radiation at the surface. But at the same time, if you increase the vegetation cover, you often have a bit higher evaporation if enough water is available. And this means that the relative contribution of the latent heat flux increases, and therefore the transport of heat decreases. And this is referred to as evaporative cooling. And this means that in some regions, increase in vegetation cover can result in warming, and other regions can result in cooling. And although we know that these kind of processes exist, they vary quite a lot from place to place. So, for example, in Northern Europe, an increase in vegetation cover usually results in warming. And at the same time, because we change the amount of transport of moisture and heat through the atmosphere, it can also impact even things like cloud formation over the restored regions. But for Africa, we don't really know how these processes work, and also we don't really know if land restoration can affect these processes. So the aim of this research was to determine how land restoration projects in Africa can impact the local climate through these biophysical processes. And although the aim of this research was not directly to monitor these SDGs, but is of course very related to life on land and also climate action, and even it kind of sees how we can tackle them both at the same time. So you can measure these biophysical effects in different ways. For example, you can use atmospheric modeling to kind of use weather or climate models. You change the vegetation cover and see what happens. But of course, we want also observational evidence for these kind of processes. Another option is to use field measurements, but in Africa, these are usually quite sparse. And also to measure these fluxes, you need quite expensive eddy covariance towers, which are only, I think, like 6 across the whole continent. So the next option is to use Earth observation, which has quite a large coverage of these kind of processes across the continent. And I use all these 3 methods throughout the project, but mainly I rely on Earth observation, which I will also explain in this talk. So I measure basically 3 things, and the first one is vegetation greenness, and this is because we want to see how land restoration projects impact the vegetation greenness, and this is kind of a first intermediate step between the land restoration and the climate effects. We also measure land surface temperature, which is related to the energy balance of the Earth's surface and also impacts the way people perceive the temperature, similarly to, for example, in cities, which we saw earlier. And we also look at cloud cover, which is a bit of the connection to the atmosphere and the climate. We can measure the greening effect of land restoration using satellite data. So this is, for example, the NDVI, which we already saw earlier. It's based on the MODIS satellite. And if we want to know the greening effect of land restoration, you can say, oh, we simply look how much greening do we see at the land restoration project, right? But the problem that you run into is that not only the restoration project itself impacts the greening, but also the climate. And especially in more the arid regions in Africa, the precipitation or the rainfall varies very much from year to year. So, for example, one year we have a lot of rain and you have a greener surface, and then the next year you have a bit of less rain, so a bit of a browner surface. And this means that we want to separate these 2 effects to really say, oh, land restoration causes greening or not. And we do this by assuming that the climate impact on greening acts on a bit of a larger scale. So, for example, if you have a restoration project and the greening is due to the climate, then you can assume that this greening also happens outside the project. So by comparing the vegetation greenness at a certain region with its surrounding area, we can kind of separate the restoration impact from the total trends. And how does this look like? Here you see a time series of NDVI over several years at the site of a restoration project, and you see that at the end of the time series you have a sudden increase in vegetation greenness after around 2017. So if we then compute the average greenness of the region around it, then you get this gray time series, and this is the difference between the 2 time series. And you can see that after 2017 we get a greening compared to its surrounding area, which we defined as kind of a local greening. And we use a trend detection algorithm to look at changes in the trends in this vegetation time series. So if we then apply the similar methodology for the whole of Africa, you get this map on the left, which kind of shows the greening compared to its surrounding area. And you see that this greening mainly happens in like the semi-arid regions of Africa. And then the next step we want to know is, do we see this greening at the location of land restoration projects? And there's not really a complete available data set of land restoration projects across Africa. So we use the WOCAT database, and it contains sustainable land management projects, which is a bit broader than land restoration alone, but it was kind of the best we had. So you see the amount of greening or local greening at these locations. And then if we compare the amount of greening at these projects, we see that the greening is higher compared to a certain reference location. So from this we can say that sustainable land management itself has a higher greening than reference regions. And if we look at a subset of the sustainable land management, for example, revegetation, which is the active planting of vegetation, then we see that this mainly results in greening for smaller regions. but also natural regeneration results in greening. So the next step was to look at how this greening impacts land surface temperature. So again, MODIS can measure land surface temperature across Africa, which you see on the map. And again, we want to kind of separate this climate effect because the land surface temperature also is impacted by things like climate change. So therefore, we apply a similar methodology. We actually just look if an area is greener than its surroundings, will it be cooler or warmer than its surroundings? And here you see a time series of the NEVI, so the corrected NEVI compared to its surroundings in green, and in blue you see the corrected land surface temperature. And you can see that's kind of a negative correlation, so in seasons where it's greener, it's actually also cooler. And then we used these kind of relationships across Africa to make a prediction on the cooling potential of land restoration across Africa. So we did this in several steps, and the first step was to create a map of potential NEVI, which you see on the left, which is basically the maximum NEVI that can be reached with certain climate constraints. And on the right, you see the change in land surface temperature this will cause if we change the current NEVI to this potential NEVI. And overall, we have a potential cooling effect because you see that quite a large regions are blue, which means if you increase the amount of vegetation, then you get a lower land surface temperature. And this is because of this evaporative cooling effect that I explained earlier. But we also see in the more arid regions that you get a warming effect. And although it's quite difficult to exactly say why this is, because we only have the satellite data, we expect that in these regions there's not enough water available to sustain this evaporative cooling effect if we increase the amount of vegetation. And then the next thing I looked at is cloud formation, and satellites can actually measure clouds, and usually if we look at the Earth surface we kind of want to remove them all, but we can also just look at them, and applied a similar methodology again. So I looked if we have a green area, does it have more or less clouds than its surrounding, and this is also because clouds and vegetation are of course very linked, so we have more vegetation in regions where it rains more. I use a bit of a different data for this, and this is because clouds are very variable through time. So I used, in this case, the Meteosat second generation satellites, which are geostationary, which means we have a very high temporal resolution. So every 15 minutes we have an image. But this also means that this is a lot of data. So I zoomed in a bit to West Africa, so the region you see here. And we looked at, again, vegetation greenness. So here you see, on the top, you see a region in West Africa. So you see parts of Nigeria and Niger and Benin and Burkina Faso. And in this region, we have a lot of protected areas, which you see highlighted at the top. And these protected areas are a bit greener than its surroundings, and this really allows us to separate this climate, this land restoration effect from the general climate trends. And on the top, you see some snapshots of cloud formation, and it's a bit hard to see, but on the left, you see, for example, quite strong cloud enhancement specifically over the greener region. But of course, we want to do this a bit more in a statistical way, so we want to calculate the overall cloud occurrence over the green areas. So we created a bit of a statistical algorithm. It's quite simple. We basically assumes that clouds are brighter than the surface below it. So we create a bit of a statistical algorithm to detect clouds. And although it's a bit simple, it works quite well. So on the top you see the original image, and then on the bottom you see the cloud mask. And if we just calculated the cloud occurrence over the past roughly 20 years, we can calculate the difference in cloud cover fraction over the green areas compared to its surroundings. And this is what you see at the graph on the bottom. So you see the difference in cloud cover over these protected areas compared to the buffer around it. So positive means you have a higher cloud cover over the green area. And then horizontally, you see the size of the projects. So the right side are the larger projects, and the left side are the smaller projects. And we actually see that there's only a statistical difference in the cloud cover fraction for the larger projects, so the green projects. And these are projects that are larger than roughly 10 by 10 kilometers, which is also roughly the size where we expect the land surface to impact the atmosphere. So for projects larger than 10 by 10 kilometers, we do see a significant cloud increase over the protected regions. So based on this, we can say that land restoration in Africa results in vegetation greening, especially in the semi-arid regions. And we also see that it can cool the local land surface temperature, but only in the semi-arid regions. So in the drier regions, it may result in a local warming effect. And the larger projects can increase cloud formation. But we also have some remaining questions and challenges ahead. For example, will this cloud formation also result in an increase in rainfall, for example? And will this then also result in more greening again? So there are some sort of feedbacks between the vegetation and the climate. Will this actually result in helping people adapt to climate change? Because this is basically just from a satellite perspective. So we literally look at it from a distance, right? And what about a biodiversity effect? So vegetation greenness is nice because we can see it across Africa, but it doesn't really distinguish between actual restoration and just, for example, monocultural tree plantations or encroachment of non-native species. So I think there are some nice results, but also a lot of challenges ahead, and I'm looking forward to diving into it in the future. So let me know if there are any questions.
Thank you very much, Jessica, for your talk. Question, wow, one from Stefano.
Hi, very impressive work first. I think it took a lot of time.
A whole PhD.
Yeah. I start from the end because you have this assessment of the cloud coverage, and that, especially when you use optical data, it impacts a lot in the assessment of the real, let's say, value that you can retrieve, especially because you're using MODIS data, so 16 days aggregated, and especially in those areas, let's say sub-Saharan area, it might happen that you have very low amount of, let's say, pixels in these 15 days or 16, whatever they are, plus the degradation of MODIS in time, plus you have used also a quite simplistic approach to cloud cover, honestly. It could be improved. Have you ever thought about using active sensors to estimate the biomass part in order to cope with the cloud coverage, especially when you have relatively small project areas?
You mean like to detect the clouds or to remove the clouds?
To assess the vegetation tenure below clouds when you have cloud coverage using like Sentinel-1 or the other SAR sensors.
Yeah, I think there was a bit of with satellite data, there's always a bit of a compromise between like the return period and the spatial resolution. And I think the problem with, for example, Sentinels was that it has a bit of a less long time series. And that's the main reason I used MODIS, because you have this like 20 years of data. And if you look at land restoration, it obviously takes a bit of time before you really start to see an effect. So yeah, I agree that none of the data sets are ideal, but yeah, that's the main reason why I used MODIS.
Yeah, Shahbaz, okay, Claire first.
Yeah, thank you very much, Jessica.
Millisecond first.
Sorry?
No, go ahead.
Ah,
Claire.
okay. Yeah, thank you very much. Very interesting. I was triggered with this small local heating effect that you pointed out. I can imagine, you mentioned that maybe due to shortage of moisture. So I can imagine the trees will not survive, but why does it lead to a heating effect?
Yes, so if you increase the amount of vegetation, you usually have a bit of a darker surface, and this decreases the albedo, so the amount of solar radiation that's reflected. So this means that more solar radiation is absorbed by the surface, in the same way that if you wear, for example, a black shirt, it feels warmer than if you wear a white shirt, for example. So it's kind of a balance between this albedo warming and the evaporative cooling effect.
But nice, you can actually see it.
Yeah.
Okay, thanks.
First of all, thank you for the presentation. That was really interesting. I had one question about one of the slides that you have. You were showing a very tight anti-correlation between an increase in NDVI and a decrease in LST.
Yeah.
Exactly that one. So my question was basically how tight is this correlation and how much it depends on the vegetation type? Because actually, there is a reason. Let me explain why I'm asking this question. So I mean, I'm basically occupy myself with the fire danger index. Okay, so with the machine learning fire danger index and LST, the land surface temperature is an important input for that. The problem is that when we do the LST, a lot of the time cloud cover affects LST in a way that the entire region, basically because of cloud cover, you cannot recover LST. And one effort to reconstruct LST was to use machine learning and other covariates to basically reconstruct what LST would have been. No? And my question was basically, how tight is this correlation and how much do you think it would be useful to use the NDVI to reconstruct LST?
Yeah. So this correlation very much depends from location to location. And the reason why I used NDVI in this study in contrast to, for example, land cover, is because in these semi-arid regions, land restoration often doesn't result in a change in land cover per se. So it's not that you first have a barren region and then you have a forest. It's more that you have a barren region, but just a bit less barren. So, but I can imagine that it changes from so the NDVI and LST are coupled differently in a forest than in a grassland region. But the map I showed is calculated using the specific correlation between NDVI and LST at that specific location. So in a way, it's a bit included, but I don't have an answer for you how it so it's exactly. Possible, but with caution. Yes.
Thank you very much, and for
Hi, thank
Melissa.
you for your presentation. I have just two questions actually. If you wanted to have a long time series, why didn't you consider Landsat? And second, since MODIS has a coarser resolution, how did you consider the border effect? So maybe the border pixels you are counting are including both restoration or restoration effects.
Yeah.
So
I used MODIS because it is a bit of a higher return period. So this means that you have less, or more likely that you have a cloud-free image. So we saw with Landsat at certain locations that there are really big gaps in the data. And the border effect is difficult, and it mainly means that we can only see restoration projects that are larger than the size of the pixels, basically.
Okay.
Yeah.
Sorry, last questions. Did you try to use other indices? Because NDVI has issues both in semi-arid areas and in very vegetated ones.
Right. We also used EVI, Enhanced Vegetation Index, and Leaf Area Index, but we did kind of a sensitivity analysis, so what would happen if we use these instead of the NEVI, but it didn't, the results are slightly different, but they're not really significant results in the spatial patterns that we see.
And we are in the tropical region where we know about you show about cloudiness and the real how reliable are optical signal in this region. So, there will, I think, we will discuss because it's very interesting what you present for many aspects, also to link to SDGs for forest ecosystem degradation, and also for carbon part, how at the end this result can be also translated in how much carbon stock you can get. It should be also very interesting to see these numbers because you can have these climate effects and how it translates practically in stock of carbon. Thank you very much, Jessica. And now we move to the last presentation of this morning, that is from Shahbaz, and on fire danger index. Shahbaz is a colleague of us at CMCC, and during the SDGs-EYES project, you see part on emission from fires, but at CMCC we have also a group working on fire risk detection, monitoring, and we have these two groups. And from one side, we are really interested to protect people and environment from fire risk, and the other part to see which is the impact or climate impact of fires on carbon cycle. Shahbaz, the floor is yours. Thank you.
Great. Thank you so much for the introduction. And thank you also for the opportunity to speak about SILVANUS here because of two reasons. One, SILVANUS is a very emotional project for me because it was my first project at CMCC. And that's one reason. The second reason is that while making these slides, I had the opportunity to really reflect on how land monitoring services can be exploited for the Fire Danger Index project, for forecasting the Fire Danger Index beyond what we already did in SILVANUS, beyond what we already do. So it was a very interesting exercise, mental exercise to actually think about it and reflect more about it. So just to explain a little bit about what SILVANUS was, what it was about. So SILVANUS basically was a Horizon Green Deal project, which ended just this year in March 2025. And just to give you an idea of the expanse of the project, that the total grant value was 19 or almost 20 million, more or less. And we were in total of 49 partners who did a lot of different, really, really cool things with this money. And the targeted impact basically was an integrated wildfire management platform. And I will explain in a while what it does, basically what it means. So the idea of SILVANUS, the main vision, was to develop an integrated technology platform targeting the problem of wildfires on many different fronts. The core of the SILVANUS is basically this diagram here. So this is what we call the integrated fire management framework. And the idea is that you basically divide the entire wildfire life cycle in a way in three phases. You have the phase A, which we call the prevention and preparedness against wildfires. There was the phase B, which we call the fire detection and the response coordination. And then there was the phase C, which we call the rehabilitability. So when the fire has actually happened, then how do you recover the forest? And this is a continuous cycle. So year on year, from one wildfire region to one firefighter season to another season, you basically continuously go in this cycle. You keep learning, you keep adapting, and you're regenerating the forest and so forth. So this is like a yearly thing. Again, just to give you an expense of how wide the project was, we had almost like 9-10 work packages occupying themselves with different things. CMCC was a big part of the work package 2 and work package 4. And there were several different things. So for example, there was virtual reality equipment, which was developed to train the firefighters to basically train them against the risk of wildfire, judging by how severe the wildfire can be in a certain season. Then there were drones, which were used for fire detection. There were robots, which were used for fire detection, coordination, also for responses. There was also a very strong part, and one of my favorite part was a social media sensing. So how could you use social media to basically properly triangulate where a fire was, based on what people are talking on Facebook, what people are talking about on Twitter. And this was something I found it very interesting, almost as much as my part. And then I will talk more about what I circle here is the ML for Fire Danger Index. And this will be the part of the presentation where I talk about how land monitoring services have been used for this particular problem. So what exactly is the Fire Danger Index? So Fire Danger Index, you can imagine as a way to quantify the risk of wildfires. So you can basically think about if a wildfire happens, what is the probability that it will happen? And in the eventuality, if it happens, what is the risk? How much severe it can get? How much damage it can cause? And in the SILVANUS integrated framework, this was the phase A, because we forecasted at least in the next few days. So tomorrow or the day after tomorrow, we forecast what is the probability of the wildfire occurrence and the respective damage from it. And why exactly is it useful? First of all, it's useful for public awareness. So you basically inform the public, you have a framework, you have a platform where we basically can inform the public what is the fire danger index of a certain region for the next days. Second, it serves as an early warning system, correlates with a little bit about public awareness, but also for the management of the resources to basically once you have an analysis of how high the fire danger index is in one region respect to the other, you can create an early warning system to inform the public which regions to avoid and to manage resources in the eventuality if it happens. So for example, if you already know that a certain region has a high fire danger index against another region, you have a better idea how to allocate the resources based on the severity of the fire or how much the fire danger index is. And the probability of fire occurrence is a very big part of judging the fire danger index, because if you basically say the probability is high, and then you talk about the danger associated if the wildfire occurs. If the probability is low, then the other factors don't really even matter. So judging correctly the probability of fire occurrence is a big part of what fire danger index actually does and what it means. And with this, you can imagine that predicting accurately where the fire can potentially happen is important. And more importantly, it's also important to localize it correctly. So for example, you have the canonical methods that are already being used since several decades on how to judge the wildfire danger in a certain region. And one of the famous method, which is very commonly used, is called the Canadian Fire Weather Index, which I show on one of the days on the left side. Now you can see that in the fire weather index map, a very big part of the Mediterranean region is under a high fire danger. So in this way, you can imagine that this map is slightly, well, let's say overestimating the risk, because of course we know that not entire Mediterranean has already burned. But so this brings me to the point that why accurately predicting the fire danger index or the occurrence of the fire is important, because the entire region, in principle, you can paint it in red, and that will be 100% probability of detecting a fire. But at the same time, from an operational point of view, this map is not very useful, because there is no way to do a differential analysis of which part of the region is at a high fire danger compared to any other part. On the right-hand side, there is an output of a machine learning model that we developed in SILVANUS. So you see that the map is actually correctly detecting 90% of the fire in the region that happened on that day, but avoiding a lot of the overestimation, specifically in this part, if you imagine. So if you look at this part here, there is only one fire, which is correctly detected, and it is very localized detection compared to the fire weather index, for example. And this is because when we use fire weather index, it's using only a subset of variables which we know are responsible for fire. So in fire weather index, you basically use the weather variables to judge how much the probability is of the fire, but that's not entirely correct because it's ignoring some variables that we already know are actually highly correlated with the occurrence of fire, which leads to this overestimation. And some of those variables are basically human contribution. So what is the human contribution in the probability of fire? What is the state of vegetation on the location where you're computing the fire danger index? And then what basically is the land cover there? So all of this information is completely missed out by the, well, not completely, but like it is missed out for the most part of the computation of the fire weather index. So before we move on, let me give you an idea about Machine Learning 101. I'm sure you have heard about this quite often, but I'll just quickly repeat it to make a point that I will make in the next slides. So in machine learning models, basically you have a bunch of different variables. In this case, for example, you can have like pictures of cats and dogs, right? And then you can basically correlate these inputs to a respective output, whatever output that may be. In this case, the correct identification of the picture, of classifying the picture as a cat picture or a dog picture. So you have two inputs, you pass it through the machine learning model, and then you basically get your desired output. So in the eventually, when you have a machine learning model trained, if you show it a picture of cat, it should recognize it as a cat with a certain high probability. If you show it a dog, it will recognize it as a dog with a certain high probability. Essentially, a machine learning model basically is learning correlations between the picture and the standard output that you wanted to, let's say, map. So it's creating, for example, this boundary between the two samples, and it's classifying these two samples in one part of the parameter, the feature space, or the other part. And of course, the model sometimes makes mistakes. So you have a yellow dot here in the blue, and then you have several blue dots in the yellow zone. So it does make some mistakes here and there. But it's basically learning how to classify it, and a good model will be able to 100% classify everything. So one way to approach the fire danger assessment problem through machine learning is to basically do exactly the same. You take a bunch of variables, for example, the weather, the vegetation, topography, anthropogenic variables, like whatever you want to put in, and you basically throw all of them in the architecture, and at the end, the machine learning model basically, for a given pixel, will learn to identify that pixel as a fire or a no fire. It will give you a probability of how likely it is the fire. And of course, these two are complementary. So if the probability of fire is P, then the probability of no fire is 1 minus P, because the sum has to be 1. But in doing all of this, the quality of data set is very important. So because in machine learning models, you can basically throw whatever data that you want, and it will by force try to find whatever correlations it can. But at the same time, whether that actually represents the reality, if the model has actually learned the underlying truth, is subjected to a question. So if you throw in garbage, it will make a correlation within this garbage, but that model will not be able to use for anything useful to make a useful prediction, because it won't be able to learn the underlying correlations that are actually there. And famously, this is called garbage in, garbage out. But why exactly am I talking about machine learning and garbage in and garbage out in this particular nice event of SDGs-EYES? So before making the point, you know all CLC. I'm pretty sure everyone knows CLC. So this is basically just to explain quickly that it basically is what is on a certain pixel. And the Corine land cover basically classifies each pixel in one of the 44 classes. And the 44 classes could be it's a urban fabric or a continuous urban fabric, non-continuous urban fabric, a forest, a shrubland, a farm, a port, or whatever. So it basically classifies in each pixel what exactly is on that pixel. And why are these two things important? 2 points to remember: garbage in, garbage out, and what CLC does. And why is it important for machine learning models? So when you do remote sensing based fire monitoring, you basically sometimes make mistakes. So for example, you see that this is the distribution of the fire samples that we use for training our model, and where those fire models have been located with respect to the CLC class, right? So the highest number of fire were detected on the CLC class 29, which is the translational woodland shrubs. Makes a lot of sense because it's actually the shrubs that catch fire and eventually they burn the whole forest. But interestingly, there are at least 500 or probably even 700 something samples found on sea and ocean, which is a very interesting result. I mean, we sometimes joke that maybe fishermen were doing barbecue and that got caught in the remote sensing. And the point is, of course, that this is what I was talking about: garbage in, garbage out. So we have to be careful when we use remote sensing based fire detection. It's either a mistake of the fire detection, it's either a mistake of the CLC aggregation method that was used to prepare the data. But the point is, we have to be vigilant what we are actually showing to the model. So in our case, in the result that I was showing, we basically use only the CLC classes painted in orange. So only the fire samples that actually come from CLC classes which somewhat makes sense in the sense of the fire danger index problem. So that's basically one thing. So we basically use the land monitoring service like CLC, for example, these products to basically do a quality test of the samples that we are actually showing to the model to filter nice fire samples from all the garbage. But we also use CLC as a direct input for machine learning. And why do we do that? Because it basically helps the machine learning model in differentiating what's on that land and what basically is correlated with the fire occurrence. So you have a way of basically kind of doing this differentiation between a high, a CLC class which has a high occurrence or high probability of fire compared to some other CLC class where the probability is not that high. And this also helps the machine learning recognize high exposure areas. So areas which are at a high exposure because they have a high content of vegetation based on the CLC class assigned to it. Then the CLC data set is basically natively at 100-meter resolution, but we don't do the fire danger index at 100 meters of resolution because we don't have the weather forecast at 100-meter resolution. So the fire danger index, which we use on machine learning, is restricted by what is the resolution of the weather forecast. Other variables you can upscale, downscale in a reliable way, but weather forecast is nonlinear, so it's not so simple to upscale, downscale the data set. So we are somewhat restricted by the resolution of the weather forecast. So if the weather forecast, for example, for us is at 2 kilometers, then we basically upscale CLC on a 2 kilometer scale based on how we want to do that. So the second point is basically vegetation monitoring in FDI and why that is important. So I point out this result, which is, well, strictly speaking, not really a SILVANUS output, but it's an interesting research that was published just this year. And the idea was that the vegetation monitoring plays a very vital role in both fire occurrence and fire severity assessment. So if you have, naively speaking, if you have a lot of vegetation, it's much likely it will burn. There is a higher probability of it burning. And it's likely to get much severe because more vegetation means more things to burn and fire can get more severe. Very straightforward. And the point is that here I show this result from the paper, which is very instructive. So on this side, the top right side, you have the fire weather index, the same one that I showed before. And on the right side, on the left side, you have the machine learning based fire danger index model presented in the paper. Here you have dead fuel moisture content, and this is total fuel load. So in this work, they explicitly take into account how much vegetation there is. So for example, how much live fuel load there is, how much dead fuel load there is in terms of the foliage, in terms of the dead trees, and in terms of the complete biomass. So there were a lot more input into their machine learning model based on how much vegetation there is that can potentially be burned. And you can see that and these white spots are basically fire occurrences on that particular day. So you can see there are several things to see here. One, that there's a high correlation between the moisture content anomaly and fuel load with respect to the fire danger index. So locations where the fuel load has been high, the fire danger index was also high generally, but not always. So if you look at this region here, it has a very high fuel load, but the fire danger index is very low. And this is important to point out because with the machine learning methods, you are able to correctly predict that maybe there is not enough people there to at least start a fire. So there might be a lot of fuel, but there is no ignition source to start a fire. So machine learning models are correctly able to differentiate between these things. And as you see here, that in fire weather index, this information is completely missed out. So fire weather index is relatively high on that location based on simply because there was a fire weather, because the weather there was basically conducive to fires. So this is one of the key differences between machine learning models and fire weather index, where fire weather index basically tells you how conducive the weather is for the occurrence of fire. Machine learning methods basically tell you correctly the fire activity that can potentially happen, not just the weather conducive for fires. And just to quickly, before I move to other slide, just to quickly say that the frequent high resolution vegetation monitoring is important not only for doing the fire danger index, but it's interesting also mitigation strategies. So for example, if you already know that there is a high buildup of vegetation in a certain area, if you have a shrubland, for example, which has a very high vegetation growth there, you could maybe encourage grazing over there. So potentially that can lower the fire danger index, which was a very classical method of basically lowering fire danger index by encouraging the cattle and grazing activity in regions where there was high buildup of vegetation. So the point being that a frequent and high resolution monitoring of the vegetation could actually help in not just for predicting fire activity, but also mitigating fire activity. And this is another slide I want to show that we already understand that humans have reshaped the landscape of wildfires such that we know that most of the activity in wildfire actually occurs because of human intervention, because of human activity. And that's fine, and well, not fine, but that is how it is. And as I was saying, that when we do fire weather index, is completely missing this information, because a fire weather index is basically what we call a process-based method. It's using physics or other kind of models to understand what exactly is the fire weather, or how conducive the weather is for fire based on some process-based methods. And in these methods, it's very difficult to take into account something so random as human activity, because there is no mathematical model to predict where there is going to be someone. And so in machine learning methods, we can do that, but there is a problem. We know for sure that the human activity is a dynamic variable, so it changes from one day to another. People are continuously traveling, moving here and there, but there is no way of tracking it. So what we do in machine learning methods is basically use proxy variables to basically somewhat include human intervention, but in a proxy way, in the sense that they are not the exact variables, but they somehow mimic the human intervention and human involvement in forest fires. And the problem with these proxy variables, for example, population density. For example, you can use the proximity to human infrastructure, nearest city, nearest road, nearest waterway. And of course, these infrastructures, they don't change on a daily basis. They change on yearly basis, or perhaps even 5-yearly basis. So these are very slowly varying variables, which give you some idea of human intervention, but not too much. And the point is basically that the land cover observations not only complement these, but can also be used to track them. So for example, typically in a lot of work related to machine learning based fire danger index, people use population density to basically track how many people there are. But CLC observations can also be used as an approximation of that. So in this picture here, what you have is basically the location of the city, so distance from a major city based on a certain population threshold, and the location of the urban fabric as classified by CLC. So you see that these blue spots that you see here, they are basically the somewhat the identification of a major city where there are at least this many people, a certain number of people are living in that. And the access on that location is basically the CLC class of urban fabric. So you see that the CLC is somewhat, and this is a very, how we say, quick and dirty picture. So it's just an approximation that a CLC land cover could also be used to identify major population spots and could potentially be used as an approximate input for a population density in a machine learning model. So I will conclude here shortly because I think I'm the only thing between you and your coffee break. So quickly concluding this. So SILVANUS was an amazing project because it approached the wildfire problems from several different fronts, and not only in the terms of basically developing tools and machinery and algorithms and everything, but also educating the people in how the firewall activity can be mitigated. So it involved a lot of citizen engagement. Then there were a lot of nice tools which were made. For example, here we have this device which basically does a real-time monitoring and real-time transmission of fire events. So you can tie this thing on a tree. If it sees a fire, it on spot processes the images and says that it's a fire and then transmits it to the local fire department. And on the map, it can point out that there was a fire detected here. Then there were robots, there were drones. Then there was very nice dashboard, which I show here, which basically shows basically all of these developments, all of these products directly on the dashboard. So if someone tweets about fire on Facebook, or not someone, if a bunch of people basically do that, the social sensing platform basically scans all these tweets, recognizes that there is a talk of wildfire somewhere, and on this dashboard you can actually see that point located. And it does it in a very intelligent way. So if someone says this concert is on fire, that doesn't mean there is a wildfire. It actually does context-based, let's say, social sensing, where it's actually really talking about wildfires and not, I don't know, Adriana, for example. Then you have machine learning-based fire danger index, and the point is that I mean, the fire weather index has been used since several decades, and it's actually very nice in the sense that it does correctly predict fire activity. But like I said, if you're painting the entire map red, it will 100% detect the fires. So the effort is not so much about, well, it is about detecting fires accurately, but more importantly, avoiding false alarms, avoiding the overestimation of the risk when there doesn't have to be, there's no risk of wildfires there. And then land monitoring services have been used in the project for example, data curation and the preparation of high quality data to train a machine learning model to detect fires accurately. Coming back to the point, garbage in, garbage out. So we basically keep the garbage out, so we get nice machine learning model to predict the fire activity correctly. Then it also serves as a direct input for machine learning models to be able to differentiate between high exposure areas and low exposure areas based on what actually is on that land, if it's a forest, if it's a shrubland. And there are several ways of basically doing that. High resolution monitoring can help machine learning models. So you can basically accurately identify high risk areas, but at the same time, frequent high resolution vegetation monitoring is also useful for mitigation strategies. If you already identify an area with high vegetation, you can maybe cordon off, or you can maybe reduce the vegetation. You can do something before the actual fire happens. And it has been used as a direct or a proxy variable for features important for the fire danger index problem. And I'm done. Thank you so much.
Thank you very much, Shahbaz. Question from Gisnio and from Rodolfo.
Hello, Shaz. So first of all, I'm not much of an expert on forest fire. So this is like I learned a lot during this presentation. Okay, so my question is that like you talked a lot like about the different work packages, like, you know, training firefighters using augmented reality, then detecting forest fires using social media. And then you also talked about the fire danger index, like basically how high the probability is for a land to get fire, but also how severe that fire can be.
Yeah.
So while doing this project in these 42 months, have you or anybody in your team thought that maybe like the concepts of SILVANUS for forest fire can be used for another, let's say, natural calamity like flood? Because to me, there is like a lot of similarity between forest fires and floods. So like the same concept can be applied for detecting floods, the probability of flood, how dangerous the flood is. And also another problem which I thought about flooding is that like when forest fire happens, I don't think that there is any soil loss that happens. But when flooding happens, there is like a high chance for soil loss, depending upon where like the city is built. Like I'm from the south of India, and the reason why I talk about flooding is that like my place is very susceptible to floods right now because of the construction. Like there's a huge dam, and then like people are building like buildings, settlements on these these mountainous areas. So when flood happens, or when like heavy rain occurs, that entire like mountain, like the entire settlement gets like washed down. So there's like a huge landslide, and like 1 year ago there was a huge landslide in a place called Wageningen, and almost like 300 people died. Like so that was one of the like biggest natural calamities that has happened in my state, and my state never like has had any natural calamity. So like, can you actually take the concepts of SILVANUS, apply it for flood, and then maybe also like extend that to detect like soil erosion for like in Melissa's pilot? Like, have you ever like anybody has ever thought of that? You can take the concepts of forest fire and apply it to like flood or any other like similar disaster.
So in SILVANUS in itself, it was just basically forest fires that we worked with, but for sure the technology, the work that we have done, the knowledge that we have developed for mitigating and for mitigating forest fires or predicting forest fires can for sure be exploited to other disasters wherever it is applicable, for sure. Whether some of the partners are doing it or not, that I do not know.
Okay, thank you.
No problem.
Thank you. Rodolfo?
Yeah, very briefly, it was a very impressive presentation, specifically on the social science part, in which you are involving people in interacting, analyzing this interaction dynamically is one of very, let's say, impressive again. No, just something that could be of your interest for the, let's say, crack of the population density or population activity, because we used the telecommunication triangle, like, you know, crowd mapping. That means that you can detect the presence of a bunch of people in a specific area with 100 meters of resolution. We had it for the city of Taranto from the telecommunication team. Is the major company for Italian telecommunication, but I don't know why they also gave us the entire data set for the entire nation for 10 years. So we have the crowd mapping for the entire nation. I think that could be useful to, let's say, retrain the model, including also the activity of the population at the national level. If you are doing it also in Italy, because I saw Greece and probably the southern Italy, you are doing something like this. We are open to, let's say, share this data to improve this type of model, if it is of your interest.
For sure. I think if that data would actually be very interesting if you have a real-time data, in the sense of, so for example, for these models, we use the yearly population density. So the population density, so to say, within a certain year, and it only changes from one year to the next year, which we basically use to track cities, where there is a big city or not. And the point is that, of course, if you have a more real-time data which can pinpoint how many people are there, perhaps on a daily basis, machine learning model will be able to basically train between them. The only point that I see here is also the fact that the areas which are served, they should have enough fire samples to train the model. So in the model that we used, that we trained, they were like, there was, I think, a 13-year data set for pretty much the entire Mediterranean region. in which case we basically have only the yearly population density. So if this data set for the Mediterranean, or even, for example, you probably have it for Italy, I imagine, no? So this data set would actually be super useful to train a model to be precisely say that there were this many people in that location, it's their fault that there was the fire.
We use it for the, let's say, health impact assessment of green, because we have the same problem with the populations, let's say, statistics, population, national statistics, population density, because it's based on year, and sometimes it's based on, let's say, retrospective data or secondary data. This is this type of data is measuring crowd mapping, so the crowds on daily base for 100 or 200, I don't remember well, resolution, spatial resolution. So I think it could be pretty useful for your model. I can share with you. We can talk about it.
That would be very, very useful. Thank you so much.
Okay. No, it's our pleasure. Thank you.
And at CMCC with Shahbaz and other colleagues, we have also this working group on fires, and we are also trying to design a framework for
actually,
risk
this data set
management.
would actually be very useful for
yes,
that
this
project
data,
as well.
yeah, we are looking also like data from Amazon, like knowing if people are there, what they are buying in during when we have fires, to see also which is the social economical type of population.
Just to quickly comment on the same thing that you were talking about, the point also is that we could for sure train the model, but at the same time, when we do want to do the inference, we should also have the data there. So for example, with this model, for example, in SILVANUS, the train model was basically deployed on the cluster. So every day it computed the fire danger index for the next day. So we should potentially be able to also have the data in real time. So if you have, for example, want to do the fire danger index tomorrow, then at least for today's fire location of people should also be there. Otherwise, or we have to do some approximation of the data set. But yeah, just to say, and I don't know how much that relates to the privacy law situations.
Those are aggregated data, and the only problem is that are not totally representative. We have to consider that are just for team operators, so people that are using that operators, but on the general population, it represents more or less 33% of the entire population.
I see. Okay, so you're not specifically pointing out one person. Okay, it's just a generalized.
It's,
okay,
it's,
I understand.
Average.
No, that's perfect. That's okay then.
I leave the Chiara. Do you have a question or comments?
Yes, a question. Thank you, Shah, so much for the very interesting presentation. So, like, actually, two little questions. One related to the how this can be operational. This fire danger index, because I guess the accuracy depends on the true positives that are detected. Even if I can see the really good improvement compared to the fire weather index, there are still a huge amount of pixels that are, red, but where fires do not occur. So in terms of like operational...
I mean, Greece still exists, so... Greece still exists, so all of Greece hasn't burned.
Yes. So but that means that when you give an alert, there will be like, like huge areas with an alert, but they won't have any fire. So because you can, as you said, like the human behavior cannot be predicted. And so like how would you see this operationalized? And the second part is about so how you model the population. This is connected to what you were saying before, but with Corinne Lancover, like are you able to see the road infrastructures? Because I see that you are modeling the distance from the urban centers, but as the Forestry Corps told us, the majority of forest fires occur next to a road. Wherever there is a road, there is probably going to be the risk of fire. So how do you see that, considering that, Corinne has its own limitation and the resolution is not so high, especially under the canopy in the forest areas, you don't see roads. So yeah, thank you.
Okay, so basically the problem is not as much of Corinne itself as the problem is of the weather variables, because even though we can get the Corinne land cover on 100 meter or even I think 10 meter resolution, the problem is that we are not actually restricted by the Corinne resolution, we're restricted by the weather forecast. So you can have the weather forecast. The one that we had in SILVANUS for the pilots was at 2 kilometers, if I remember. The data set that we use for training is at 1 kilometer. So, and in 1 kilometer picture, there are already at least 1,000 of CLC pictures, or no, yeah, it's almost like 1,000 because you have 100, and then you're basically upscaling it to 1 kilometer. So you're kind of like, you are basically upscaling the information in some way. Either you were doing some kind of aggregation or you're doing some other strategy. We have a different strategy. We didn't use aggregation. So you basically somewhat are less sensitive to the individual structures as on the higher resolution as you are on a lower resolution, but you cannot actually go to the lower resolution. So in an operational way, what we basically do in SILVANUS, I mean, what we did in SILVANUS is to basically say that we have a model, and then you basically use the CLC variables, upscale it to the same resolution as the weather, and then use that as an input. And the way that we did this was to basically subgroup or map the 44 CLC classes into another subgroup, which were representative of generally what was there. So we have one group which takes into account the shrublands, the forests and everything, and then you have the percentage of how much that class is on that particular variable. So for example, the cities and the airports and the ports, we don't care about them. So we put all of them in one group. And that group will be classified machine learning model as being as the lowest probability of fire being occurring there. Then you take the vegetation and you group them all in one class, one kind of vegetation in one group, and then another group, and then so forth. So you basically do a regrouping of the classes. And you basically do is that how much percentage of that class is in that 1 kilometer pixel taken from the 100-meter resolution. So you basically do some kind of a upscaling, not exactly aggregation, but like some of a remapping of it, which gives us some flexibility in actually identifying individual features as well, because you can make the groups more explicit where you want to, and you can make them more obscure if you want to. And operationally, we basically use the same CLC that we have for the last 2018, I think, and we basically reuse them to compute it again if we want to compute the fire danger index for tomorrow, for example.
But maybe Fabio, and a very quick question because we have to move.
Yes. Thank you for the presentation. Very interesting. Just one question about the models. So
sorry, about
the model that you are here using. So if I correctly understood, basically your model is an improvement compared to the previous one because Greece was not on fire, or all Greece was not on fire. So
yeah.
The question is, the result of this model is comprehensive of the human factor in the way that we are trying to model, and if yes, you have just one model that included the human factor, or you have estimated two models, one with a fire that are not related to the human factor, and one for the fire that are related to the human factor. So, thanks.
Okay, so that actually is a great question. We have, during the process of actually getting to this model, we do have some models in which we, for example, remove some of the variables from the training process. And we immediately see, for example, an overestimation. And the overestimation is basically because, for example, I don't actually explicitly remember if we ever did that with population density itself as such, but we did it, for example, with NDVI. So if we remove NDVI from the training process, there is obvious overestimation of the risk, because it's basically saying that a place is burnable when there is no vegetation, because during the model training, the model was never able to build a correlation between the amount of vegetation and the occurrence of fire. So if it's missing this information, it will also miss the information that it might be saying something at the high probability of burning when there actually is nothing to burn. So we have this, and it was somewhat of actually an accident because we actually input the wrong NDVI, for example. So in actually one of the experiments, the NDVI was incorrectly estimated to be 0 everywhere. And the fire danger index was 0 everywhere and we were like, whoa, that's fantastic. We actually don't have any fire danger index. But it turned out that it was actually a fault of the NDVI being underestimated. So I imagine that if you remove variables like population density, it won't be able to build the correlation between how many people there are and how likely there was a fire over there. Without this correlation, it will still give an overestimation, maybe not at the same level as fire weather index, but it will still give you an overestimation.
Thank you very much. I'm sorry if I have to interrupt here this very fruitful discussion. But we have to move to take a break of 10 minutes and come back for the roundtable discussion.